Welcome back. Problem 1.66. So statement is the 2000 pound load may be moved along the beam BD to any position between stop E and F. Knowing that allowable stress 6 KSI for the steel rod in A, B and CD, determine where the stops should be placed if permitted motion of load is to be as large as possible. So you can see this is the beam BD and there is a load of 2000 pound that is acting between this stop E and F. Clear? So you have to find this stop to be placed at distance of XE and XF so that this load can be maximally or large as can move as large as possible. So let's start with the solution. Load is given as 200 pound. Clear? The allowable stress for this rod BAB and CD is given as 6 KSI. Diameter of this rod is half inch while this rod is 5 or 8 inch. So first what we will do is that we will find the force due to this load P, that is downward. We will having a force in AB and this rod CD. Let this is FCD and this is FAB. So by we have been given as allowable stress is 6 KSI, which is maximum stress. We know that allowable stress is equal to force per unit area. So for rod AB, we have this allowable stress is equal to force AB divided by area of AB. Now we need this FAB, so FAB will be equal to force in rod AB will be equal to allowable stress into area of AB. Clear? So this FAB will be equal to sigma allowable, which is 6 KSI. So 6 multiplied by this area of this rod having diameter 6 by 2 inch is equal to pi by 2. Clear? Pi by pi by 4. Area of rod is equal to pi by 4 d square. So pi by 4 multiplied by d is 1 over 2 square. So when you solve this, you will get FAB comes out to be 1.178 kips. This is FAB. Similarly, this FCD, which is this one, will be equal to allowable stress into area of CD. So allowable stress is 6 and the area of rod CD is pi by 4 into D, which is 5 by 8 whole square. So again, when you solve this, you will get FCD will be equal to 1.84 kips. Now you have both FAB and FCD, so you will have to find uh, this distance XE and XF so that this load is to be longer, can be moved as longer as possible. So what we will do is that we will draw the free body diagram. So if I draw the free body diagram of this beam, so it will be like this. Clear? Here you will be having this FAB and here you will be having FCD. The total length is 60. So length from here, this is 60 inch. Clear? Now if this load is at a distance of XE, for example, let this is your XE. This is your XE. If your load is at this position, this P, 2000 load, P is equal to 2000. So you can see that total distance is 600. So this distance will be remaining, this distance will be equal to 60 minus XE. So what we will do is that we will apply equilibrium condition. This is your point B and this is your point D. So by applying equilibrium condition, that sum of all movement about point D is equal to 0 and taking the counterclockwise movement as positive. So about point D, one moment is due to FAB into perpendicular distance is 60 and it is producing clockwise, so it will be negative. The second moment is due to this 200 and perpendicular distance is 60 minus XE and this is producing counterclockwise, so it will be positive. So their sum must be equal to 0. So I will write minus 60 into FAB plus 2000 into 60 minus XE must be equal to 0. So you know that you have FAB is 1.78 kips, so you can you have to convert it. So I will write minus 60 into FAB is 1.178 into 10 raised to power 3. Clear? That will be convert into pound and plus 2000 into 60 minus XE is equal to 0. So this 2000 into 60 minus XE will be equal to 60 into 1.17810 into 10 raised to power 3 divided by, if you want to convert, if you divide 2000 on both sides, so we will left with 60 minus XE is equal to 60 into 1.17810 into 10 raised to power 3 divided by 2000. Clear? And you will get this value will be equal to 35.343. Clear? So we are interested to find out XE. So XE will be equal to 60 minus 35.343, which will give you 24.7 inch. So this is the one position of the stops. Clear? Now what if we move this load to this point F and we draw the free body diagram just like we have drawn earlier. So this is the beam. For example, this is the beam. This is your FAB. This is your FCD. Clear? Now you have this distance where the load is applied. Clear? And that is 2000 load. Total length is 60, and here this is position of the second stopper, that is XF. I will show you. This is the XF. Now again, this is your point B and this is your point D. You can apply the equilibrium condition, the second equilibrium condition, which one is that sum of all movement about point B is equal to 0 and taking the counterclockwise movement as positive. So about point B, one movement is FCD into perpendicular distance is 60. Clear? And the second movement, this FCD into 60 will creating counterclockwise movement, so it will be positive. The second movement is due to this 2000 into perpendicular distance is this XF and this is producing clockwise, so it will be negative. Their sum must be equal to 0. So I will write 60 into FCD minus 2000 into XF is equal to 0. So it means that 2000 XF is equal to 60 FCD. So 60 multiplied by FCD is 1.84 kips. 1.84 into 10 raised to the power 3 is equal to 2000 XF. So XF will be equal to 60 into 1.84 into 10 raised to power 3 divided by 2000. So from here you will get this XF comes out to be 55.2 inch. And this is the position of the second stop. So we will conclude that you have to put this stop E at a distance of 24.7 inch 24.7 inch from this end, and XF this stop at a distance of 55.2. So this gap where this weight can be moved, can be traveled, will be the maximum distance. And this was all about problem 1.66. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1.67. So statement is, knowing the force P of magnitude 750 Newton is applied to pedal as shown, determine the diameter of pin at C for which the average shear stress in pin is 40 megapascal. B part is corresponding bearing stress in pedal C and corresponding bearing stress in each bracket. So you can see this is a pedal where a force of P is applied. The P is 750 Newton. Clear? This is the frontal view and this is the side view. Now at this point C, you can see this is pedal portion. So you have to find this diameter of this pin at C in first part, for which the shearing stress is 40 megapascal. Then you have to find the corresponding bearing stress in this portion. Clear? And in bracket you have to find the corresponding bearing stress. So let's start with the solution. Now due to this load, definitely there is a reaction force due to this rope. Let this is FAB, and at point C, as this force cause it to down, clear, causing this uh, to have a reaction force like this, and at point C we will be having a reaction force C in this direction, that is resultant. So I will represent this C is like this. You can also draw its two component, that is one is Cx, another is Cy. Clear? And this is C. This is the resultant. So how you will find this resultant? You can see that if I draw dotted line, so this distance is 125 and this distance is uh, 300 millimeter and this height is 125. Clear? So by using Pythagoras theorem, this distance will be equal to this distance, which is, let this point is E. So we will find CE. So CE will be equal to 125 square plus 300 square. So it will be equal to 325 millimeter. This distance is 325 millimeter. Now what we will do is we are interested to find out this C. So this C can be found by using equilibrium condition, that sum of all forces along y direction must be equal to 0 and force upward taken as positive. So you can see we have three forces. One is P, that is downward. The second is this vertical component. So how you will find this vertical component? So definitely you can see if this angle, if this is making theta angle, clear, so its component CY will be equal to C into sine of theta, C into sine of theta, and sine of theta is, if this is theta, so sine of theta is 125 by 325. So C into 125 by 325. This is the value of Cy. Clear? So sum of all forces along y direction must be equal to 0. So minus P plus Cy is equal to 0. So from here Cy is equal to P, and since Cy is equal to C into 125 by 325 is equal to P. So P is, so from here you will get C is equal to 2.6 times P. Now you have the value of P, 2.6 multiplied by P is 750. So it will give you C. So C will equal to 1950 Newton. Okay, now you have this C. You can see here that C will applied over here, clear, and this C will cause double shear in this diameter. And also we have been given as allowable shearing stress, for this pin is given as 40 megapascal. And since it is causing double shear, therefore single force, shear force, will be equal to 1/2 times C. So we know that shearing stress in this pin is equal to shearing force. So here that will be equal to half C, because you can see one force and it is producing double shear. So we'll take half of C divided by area of this pin. So area is pi by 4 d square. Okay, so pi by 4 into d square, because d is not known, clear. So you can just put the value over here. D square will be equal to C 2C over pi into shearing stress in pin. So from here D will be equal to under the root 2 into C divided by pi into shearing stress in pin. So put the value 2 multiplied by C is 1950 divided by pi into shearing stress is 40 megapascal. So 40 into 10 to the power 6 under the root. So when you solve it, you will get required diameter comes out to be 5.57 into 10 to the power minus 3 meter, and in term of meter this D will be equal to 5.57 millimeter. So this is the required diameter of pin at point C. So this diameter is D, and this is equal to 5.57 millimeter. Now if you look at this point, clear, this point, so this shaft will be having the diameter this, so we will find bearing area. So bearing stress, so bearing stress is equal to bearing force into divide by bearing area. So if you have a hole, three-dimensional hole, clear, so this bearing area will be equal to pi d into or 2d into t, d into t, sorry. So we will find the second part, bearing stress. So bearing stress is equal to force. Here the force is C divided by bearing area. So C divided by bearing area is D into T. Because you can see that if you have a plate of some thickness and there is a hole, clear, so you will be having bearing stress area, bearing area will be equal to the diameter of this, which is diameter of this pin, into this thickness T, clear. So you can just put the value. Bearing C is 1950 divided by diameter of this hole in which this pin is inserted is 5.57. So 5.57 into 10 to the power 3 will convert it into meter, multiply by thickness. Now thickness of this is given as 9 millimeter. So 9 into 10 to the power minus 3. So when you calculate it, you will get the bearing stress in this Paddle at point C will come out to be 38.9 into 10 raised to power 6 Pascal, or that is equal to 38.9 megapascal. So this is the bearing stress at point C in paddle, in this portion, in this paddle portion, clear, in this portion. Now what we have to find is, in third part you have to find the bearing stress in each support bracket. So you can see this is the support bracket and this is the bearing, spin. So you have to find the bearing stress in that. Again, this is your third part. So third part is equal to bearing stress is equal to force per unit bearing area. So C is 1950 into diameter of pin is 5.57 into 10 raised to power minus 3. And what about thickness of this bracket? So you can see the thickness of this bracket is 5 each, 5 millimeter each. So you have to put 5 into 10 raised to power minus 3. So when you solve this, you will get bearing stress comes out to be 35 into 10 raised to power 6 Pascal, and in megapascal it is 35 megapascal. So this is the bearing stress in each bracket at point C. So in here you will be having a bearing stress is 35 megapascal. And this was all about problem 1.67. I hope you are enjoying my videos and you are learning from it. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest video. If you have any question, kindly let me know. I will try my best to answer you. Thank you for watching. Welcome back. Problem 2-25. So statement is each of link A, B and CD is made of aluminum. E is 10.9 into 10 to the power 6 psi and has a cross-sectional area of 0.2 square inch. Knowing that they support the rigid member BC, determine the deflection of point E. So this is rigid member BC that is supported by two link A, B and CD. The load at point E is 1 kip. So what we have to find? We have to find the deflection of this point E. So let's start with the solution. So you can see here that due to this load there will be a tension in this member AB and CD, but if you want to remove this, so there will be a reaction force of these two links. So we will draw the free body diagram of this rigid member BC. So what if I draw it like this? Assume that if we draw like this, so at this end we will having a force which is represented by FAB. Clear? This is your point B and this is your point C, and here you will be having a force that is represented by FCD, and at this point we have a load of P that is acting downward. This distance is given as 10 inch while this distance is given as 22 inch. So by applying equilibrium condition we can find this FAB and FCD. So first equilibrium condition is sum of all moment about point C is equal to 0 and taking the counterclockwise movement as positive. So about point C, one moment is FAB into perpendicular distance is this 32 inch and this is producing clockwise, so it will be negative. And the second moment is due to this P into perpendicular distance is this 22 and that is counterclockwise, so it will be positive. So their sum must be equal to 0. So I will write FAB into perpendicular distance is 32 and this is minus plus P into 22, clear, is equal to 0. So it means that FAB is equal to 22 multiplied by P. P is given as 1 kip, so I will multiply 1 into 10 raised to the power 3 divided by 32. So from here you will get FAB is 687.5 pounds. Now you can find FCD by using another equilibrium condition, that sum of all forces along y direction must be equal to 0 and taking the upward force as positive. So one force is FAB, which is 687.5, that is upward, minus P, which is 1 kips, so 1 into 10 raised to power 3, plus FCD is equal to 0. So again, when you solve this, you will get FCD is equal to 312.5 pounds. Now you have both this FAB and FCD. You can see that due to this load, clear, due to this load, there will be a tension in link AB and CD. So definitely there will be elongation, change in length of AB, and there will be a change in length of CD. So what we have to find this change in length. So elongation in link AB is given by change in length of AB is equal to force AB into length of AB divided by E into A. So you can see force in AB is equal to 687.5. So 687.5 multiplied by length. Length is 18 inch. So into 18 divided by E is given as 10.9 into 10 raised to power 6 psi, and area is this one. So 10.9 into 10 raised to power 6 multiplied by area is 0.2. This will give you change in length of AB. Now when you calculate it, you will get 5.676 into 10 raised to power minus 3 inch. And we can call it change in point B, because this point B will move downward. Clear? Now elongation in link CD is represented as change in length of CD is equal to FCD into length of CD divided by E into A, because these are the same material. So E and A is same. E and A is same, yes. So FCD is 312.5 into length is again, that is 18 inch. Both lengths are same. This divided by E, which is 10.9 into 10 raised to power 6 multiplied by area, which is 0.2. That is CD. When you calculate it, it will be 2.5803 into 10 raised to power minus 3 inch. Since this is point C, the C will also move down. So I will call it del C. Now you can see that this point B will move how much? That is del B, and that del B is 5.67 into 10 raised to power minus 3, while this point C will move del C, and that is 2.5803. It means that due to this loading, this stretch will be like this. This will be like this, and your this rigid beam will be tilted. So what we will do is that if I draw the deformation diagram, so how we'll draw deformation diagram, I will write it, deformation diagram. So if I represent link BC is like this is your point B, this is your point B. Now you can see that point B will change in length of the link B, or point B will move to this point, and that is represented as del B. Clear? And del B is 5.67 into 10 raised to power minus 3, while point C will move this much distance. So let this point is this. This is your del C. which is 2.58 into 10 to the power minus 3. And this will be the rigid bar will be this one. So this is your point B dash, and this is your C dash. Here this is the point where load P is applied there. So definitely if I forward it or I extend it, so this is your new point E dash. So and we have to find this deflection of point E. So what we will do is that you can see that if I draw a horizontal line from this point, clear, if I draw it horizontal point line from this point, so you can see this distance BC is this same del C, and here we have a theta which is represented as theta, clear, that is slope. How we will find this slope? So this slope delta is equal to what this will be equal to by using S is equal to R theta, clear. So you have this is S, sorry, theta is equal to S over R. So for here you will have this S. So this distance, let me show you, this distance is equal to so this distance is equal to total del B minus del C will give you this distance, clear. And what is R? So R is this one, which is the length, total length, LBC. So I will write it as del B minus del C divided by LBC. So if you subtract del B, which is this one, from this, if you subtract del C from del B, so you will get 3.096 into 10 to the power minus 3 divided by length of BC, which is total 32. So I will write it 32. So when you solve this, you will get theta is 96.759 into 10 to the power minus 6 radian. Now you have this theta. Again, you can see you have this theta. So you can find this deflection or del E. I will write it as del E. From this point, this to this point, this is del E. So you can see this del E is equal to, up till now, this distance from this to this is equal to del C. So I will write it del C plus remaining this distance from this point till this point. This distance is, you can see this will be LEC into theta. By using this formula, S is equal to R theta, I will show you this distance will be equal to this theta multiplied by this length will give you this distance. So I will write it LEC into theta. So del C is 2.5803 into 10 to the power minus 3 plus LEC is 22 inch. So we will write 22 into theta is 96.759 into 10 to the power minus 6. So when you solve this, you will get deflection of point E comes out to be 4.7090 into 10 to the power minus 3 inch. And this is our answer. So you can see that due to this loading, this point B and C, point B will move to this and point C will move this, and this will be the behavior of this rigid link. So this is deflection of point E. I hope you have enjoyed this video, and if you are new to my channel, then subscribe it and press the bell icon so that you can get notification about latest video. And if you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1.15. So statement is when the force P reached 8 kilonewton, the wooden specimen shown failed in shear along the surface indicated by dashed line. Determine the average shearing stress along that surface at that time of failure. So you can see this is the load P that is applied, that is tensile load 8 kilonewton, and it is given that due to this load the wooden specimen shown failed on this dashed line. Clear? So you have to determine the shear force along that failure. So let's start with the given data. So we have been given that P is equal to 8 kilonewton. Clear? And what we have to find is that we have to find the shearing stress tau along the dashed line which caused failure. So what we will do is that you can see that this is the length if I draw it like this. Clear? And the width is given as 15 millimeter. So width is 15. So it will be like this. This is the area, shear area, and that is equal to 15 multiplied by 90, and that is 3050 square millimeter. And the shear force acting on this area will be equal to P, and that is given as 8 kilonewton. So solution is that area being shared where this failure caused is equal to 15 millimeter multiplied by 90 millimeter, and that is equal to 1350 square millimeter. And the load which is 8 kilonewton, so 8 into 10 raised to the power 3 Newton. So we know that shearing stress is equal to shear force divided by shear area. So force is given 8 into 10 raised to the power 3 Newton divided by area is 3050 square millimeter. So you will get 5.93. Okay, let me clear one more thing is that this 8 into 10 raised to the power 3 Newton, and if you convert it into meter, so 3050 into 10 raised to the power minus 6 square meter. So you will get the shearing stress comes out to be 5.39. So you will get the answer will be 25925.92, and the unit will be Pascal. So if you convert it into megapascal, so shearing stress will be equal to 5.92 into 10 raised to the power 6 Pascal, and that will be equal to 5.92 megapascal. So 5.92 megapascal is the answer for this question. This is the shearing stress, average shearing stress along the surface at the time of failure. And that was all about problem 1.15 taken from Mechanics of Material by Beer Johnston 6th edition. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and hit the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1.16. So statement is the wooden member AB are to be joined by plywood splice plates that will be fully glued on the surface in contact. As a part of the design of the joint and knowing that the clearance between the end of the member is to be 1/4 inch, determine the smallest allowable length L if the average shearing stress in the glue is not to exceed 120 psi. So you can see this is wood A and this is wood B that is glued together with these plywoods. The gap or clearance between A and B is 1 over 4 inch, and allowable shearing stress in the glue is 120 psi. So you have to find the allowable length L. So we have to find this L length L. This is the length. So let's start with the solution. So if you look at, if I draw this wood A, if from frontal view, this is A, and let's say there is a small gap, and this is would B. Clear? And these are the two plywood pieces. Same is over here. Clear? So now you can see that this is the load. 5.8 kips is applied. I will show it over here. This is the load P, which is 5.8 kips, and same with the upper one, 5.8 kips. So you can see that there are 4 areas. One is this one, the second one is this one, third one is this one, and fourth one is this one. So these are the 4 separate areas that are glued. So what will happen is this load will be distributed. I will show with in white color. So due to this, the load in B will be in this direction. Load in B will be in this direction. Clear? And here it will be also in this direction. In A, it will be opposite to this load, and the load in this upper one, this will be F. Let this is F. So same load that is glued with this surface will be also opposite to this force, and this will be in this direction. Here it will be in this direction, and here this will be in this direction. Same is the case in this direction and in this direction. So I will write that there are four separate areas that are glued, and each of these areas transmits one half of 5.8 kip force. I will repeat it. You can see this is the load 5.8 and this is 5.8. So here this total load will, this F2F will be equal to 5.8. So 2F will be equal to 5.8 kips. So F will be equal to 5.8 divided by 2. Now we have this force, and this length is the total length which we are interested to find out. Clear? Let this length, this small length, this portion length is represented as small l. So I will show, let this length is small l, which is glued. So I will write let L is equal to length of one glued area, and width is given as, you can see width is here, this is 4 inch of this plywood. So width is 4 inch. So area will be equal to length into width. So it will be equal to 4 times L. Now average shearing stress tau is equal to shearing force per unit shearing area. So this is the shearing force F and per unit area. And this tau is equal to F by A. So we are interested to find out area A. So area is equal to F divided by tau. And this area is equal to 4L, clear, 4 into L. So F over T. So this small length L, glued length, will be equal to F divided by 4L. So F is given as F we have found 5.8 divided by 2, 5.8, 5.8 kips. So we'll convert it into 10 to the power 3 divide by 2, clear, and divide by 4 times. This is 4 ta, 4 times ta, and ta is given as 120 psi. So when you calculate, you will get this length will be equal to 6.0417 inch. So it means this length is 6.0417 inch. Now you can see that total length L will be equal to, you can see this is the total length L, which is equal to small l plus this gap C and the same this small length L. So it will be equal to 2 times L plus C. So you can just put the value 2 into 6.0417 plus C. C is 1 over 6, 1 over 4 inch. That is given 1 over 4 inch, which is 0.1 over 4 inch. So after calculating, you will get the total length required will be equal to 12.33 inch, which is the answer. And that was all about problem 1.16. We have calculated this total length L, and I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and hit the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you. Welcome back. Problem 1.17. So statement is a load P is applied to steel rod supported as shown by aluminum plate into which 0.6 inch diameter hole has been drilled. Knowing that shearing stress must not exceed 18 ksi in steel rod and 10 ksi in aluminum plate, determine the largest load P that can be applied to the rod. So you can see this is the steel rod, clear, where P load is applied, and this is the aluminum plate that is used to support this steel rod. There is a 0.6 inch hole drill in this aluminum plate, and the diameter of steel is the upper portion of steel rod is 1.6 inch. So you have to find the load P. The shearing stress, allowable shearing stress for steel is 18 ksi and for aluminum it is 10 ksi. So let's start with the solution. We know that shearing stress is equal to shearing force per unit area. So for this steel plate, if you look into it, this P load is applied, so definitely this will be the shearing area. And if I draw it like this, so this area will be equal to pi d, and thickness is 0.4 into T. So I will first find for steel shearing area will be equal to pi d into T. So pi multiplied by d is 0.6 inch, clear. Again, this will be the dia where this steel rod may shear, which is 0.6, and thickness is 0.4. Okay, So when you calculate it, you will get the shearing area for this steel rod comes out to be 0.7540 square inch. Now we know that shearing stress in steel is equal to shearing force per unit shearing area. So what we will do is that we need P. So P will be equal to shearing stress in steel into shearing area. So P will be equal to shearing stress in steel is 18 ksi. So 18 multiplied by area is 0.7540, and when you calculate you will get that will be equal to 13.57 kips kilo pounds. So this is for steel. Now what we will do is that we will find the same for aluminum. We know that shearing stress in aluminum is equal to shearing force per unit shearing area. So area for this, now you can see these plates, this aluminum plate supports. So shearing area will be this one. This will be the diameter. Clear? And this diameter is 1.6 and thickness of this plate is 0.25. So again this will be pi d into t, pi d into t. So pi is 3.1417 multiplied by diameter which is 1.6 and thickness is 0.25. So when you calculate it will be equal to 1.2566 square inch. Okay. Now put the value again. We will get from here we will get P will be equal to ta allowable ta allowable in aluminium into A. So P is equal to shearing stress in aluminium into A. So put the value shearing stress in aluminium is 10 ksi. You can check it. So 10 multiplied by this area is 1.2566 and that will give you 12.566 kips, or that is nearly equal to 12.57 kips. Now you can see you have two loads. Either you can apply this load or this load. So we will choose, always we will choose the less one. We will choose smaller value of P. Why? I will show you in a while. P, and that is equal to 12.57 kips, which is the answer. Now I will explain the reason why we choose the smaller one. Let we choose this value P. Let P is equal to 13.57 kips. And we know that top aluminium shearing stress in aluminium is equal to shearing force per unit area. So 12.57 divided by area of aluminium, which is 1.2566. Clear? And that will give you 10.79 ksi. Okay. If you look that this is the 10.79 ksi shearing stress will develop in the aluminum, which is greater than allowable shearing stress in aluminum, and that is 10 ksi. So it means that due to this load it will fail. But using this smaller value of P12.5, it will satisfy aluminum as well as for steel. So that's why we choose the smaller value of P, and this is our correct answer. And that was all about this problem 1.17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos and channel with your friends so that they may also learn mechanics of material. Thank you for watching. Welcome back. Problem 1.14. So statement is a couple M of magnitude 1500 Newton meter is applied to the crank of an engine. For the position shown, determine the force P required to hold the engine system in equilibrium. And in part B, the average normal stress in connecting rod BC, which has 450 square millimeter uniform cross section. So you can see this is the piston that is attached to the crank, and at the end of crank a moment M 1500 Newton meter is applied. So you have to find this P for equilibrium position, and then average normal stress in this BC. So couple is given, you have to find force and average normal stress. So let's start with the solution. You can see here in this diagram, if you remove the support or shaft from this crank, so definitely there will be a reaction force. This reaction force, vertical reaction force is AY, and horizontal reaction force is AX. Let me correct it. Okay, so this is AX, and there will be a reaction force from this side of the engine block, and this force is horizontal force. So we'll find this horizontal force, and you can also find AX and AY. So what we will do is that we will apply equilibrium condition. I will write using piston rod and crank together as free body diagram, and we will find this H. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So these two forces do not produce the moment because it is passing through point A, and this P force is also passing through A, so it is not producing movement. Only force producing movement is this horizontal force into perpendicular distance is this one, which is 200 plus 80 to 80 millimeter. So I will write H multiply by 280, so in meter it is 0.280 meter, and this is producing, you can see this is producing counterclockwise movement, so it will be positive. Another movement that is clockwise, which is plus M minus M, will be equal to 0, and minus moment value is given as 1500. So from here you will get this H horizontal force will be equal to 5.3571 into 10 raised to power 3 Newton. Now what we will do is that we will find this length of rod BC. So what I will do is that you can see you have a P force that is acting downward. So I will draw it. This is the P force that is downward. Clear? And there is H, which is at a distance of 60 millimeter from this edge, 60 millimeter. So by using head to tail roll, this is H, this is H. So by using head to tail roll, this will be the resultant, which is actually this length of BC. You can see that this is the P, this is the H, and this is the resultant. And this will be also the resultant force acting on it. So I will write it here. This is the length BC, but we will also calculate the force BC. So this height is given as 200 millimeter. This is 60 millimeter. So let this is triangle A, B, This is point C, this is point B, and this is point M, for example. So we have triangle BMC. So in triangle BMC, FBC square is equal to H square plus M square. Also, if you want to find the length, so length of BC square is equal to 60 square plus 200 square. So from here LBC will be equal to under the root 60 square plus 200 square, and you will get length of BC will be equal to 208.81 millimeter. So this is the length. This is the length of this rod BC. Now what we will do is that you can see you have the triangle for finding the force PH and FBC, as well as, so by using force triangle, what we will do is that if you take the ratio P divided by H, so P divided by H will be equal to 200 divided by 60. So this is 200 and this is 60. So 200 divided by 60. So from here you will get, you have H which is 5.37. So you will get P will be equal to 200 into H divided by 60. So you can just put the value of H. So 200 multiplied by 5.357 into 10 raised to power 3 divided by 60. And you will get P, the value of P for equilibrium comes out to be 17.86 kilo Newton. So this is the load. Now again you can see that if you consider this piston separately, so there is horizontal force, you have the value of P, and the reaction force will be in this direction, FBC, from this force triangle, So you will get the C. Now what we will do is that if you take the ratio FBC over H, so definitely this length is known and this length is 208.81 divided by H is given as calculated as 5.375 into 10 raised to power 3. So here, from here you will get this force FBC will be equal to 18.64 into 10 raised to power 3 Newton. Now again you can see this this force is in this direction, clear. So member BC is in compression. So rod, what I have to write is that rod BC is a compression member, and area which is given as 450 square millimeter, and that in meter it will be 450 into 10 raised to power minus 6 square meter, and we will calculate the average shear stress in rod BC, which is equal to minus FBC, because this is in compression, divided by area, and the area is given as 450 square millimeter. So you can just put the value 18.64 into 10 raised to power 3 divided by this area 450 into 10 raised to power minus 6, and you will get the result 41.4 into 10 raised to power 6 Pascal. Or you can say average shearing stress in BC is equal to 41.4 minus 41.4 megapascal. So This is the answer of our second part, and that was the answer of our first part. And that was all about this problem 1-14 taken from Mechanics of Material by Beer and Johnson. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the. Welcome back. In this video we are going to solve problem 1.20 and 1.21. So we'll start from 1.20. The statement is the axial force in column supporting the timber beam shown is 20 kips. Determine the smallest allowable length L of the bearing plate if the bearing stress in timber not exceed 400 psi. So you can see this is the column support having a load of P which is 20 kips. This is the bearing plate and this is the timber beam which is supported by this bearing plate and this support column supporting. So load is given, bearing stress is given, so you have to determine this smallest length of the bearing plate. The width is given as 6 inch. So let's start with the solution. So we know that bearing stress is equal to load per unit bearing area. So first you can see from here that bearing area, this bearing plate is in contact with this timber beam. So this area is width into L, which is L into 6. So bearing area will be equal to AB will be equal to length multiplied by 6, which will be equal to 6 times L. Now we have P, we have sigma B, which is given as, so AB will be equal to P divided by bearing stress. So P is 20 kips, so 20 into 10 raised to power 3 divided by bearing stress, which is equal to 400 psi. So 400, and that will be equal to AB. So AB is equal to 220 into 10 raised to power 3 divided by 400. So we know that AB is equal to 6L. So 6L will be equal to 20 into 10 raised to power 3 divided by 400. So from here you will get L will be equal to 20 into 10 raised to power 3 divided by 400 multiplied by 6. So when you solve this, you will get this minimum length of the bearing plate will be equal to 8.33 inch, which is the answer of this question 1.20. Now we'll move toward the second problem, and the statement of this problem is an axial load P is supported by a short wide flange beam which is W8 into 40 columns of cross section area is 11.7 square inch and is distributed to concrete foundation by square plate as shown. Knowing that the average normal stress in column must not exceed 30 ksi and the bearing stress on concrete foundation must not exceed 3 ksi. Determine the side A of the plate that will provide the most economical and safe design. So you can see this is W column 8 into 40 and the load P is applied. This is the foundation and this is the bearing plate having side A by A. In given data, it is given that normal stress in this column must not exceed 30 ksi and bearing stress on concrete foundation is 3 ksi. So let's start with the solution. So what we will do is that first we know that normal stress or average normal stress or normal stress is equal to load per unit area. So this load is given, this load P is not given and average normal stress is given. So we will find first this P. So P will be equal to average normal stress in column multiplied by the area. Area is given as this and average normal stress is this. So 30 into 10 raised to power 3 multiply by 11.7, which is the area, will give you load, and when you calculate it, it will be equal to 351 kips. So now we have this load. What we will do is that we will find the bearing area. Okay, so we know that bearing stress is equal to load divided by bearing area. Clear? So this is the bearing area. This bearing plate of A by A is in contact with this foundation. So bearing area will be equal to A multiplied by A. Okay. So from here you will get this bearing area will be equal to P divided by bearing stress. So P we have find out 351 kips. So 351 divided by bearing area, which is given as 3 ksi. So divide by 3 will give you the area, which is equal to 107 square inch. Now this is the bearing area which we have calculated 117 square inch, and we know that this is the square plate. So area will be equal to AB, which we have calculated is A by A, which is equal to A square. So here we will write area of bearing plate is A square, which is 117 square inch. So from here you will get A will be, if you take the square root on both sides, so you will get this A, which comes out to be 10.82 inch. So this is the minimum size of this bearing plate, 10.82 inch into 10.82 inch, which satisfy the above condition. And that was all about these two problem, 1.21 and 1.20. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video which I post. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1.23. So statement is a 5 by 8 inch diameter steel rod AB is fitted to a round hole near end C of the wooden member CD. For the loading shown, determine the maximum average normal stress in the wood, the distance B for which the average shearing stress is 100 psi on the surface indicated by dash line, and C average bearing stress on the wood. So from this figure you can see this is the wood and this is rod AB that is made of steel. The load on this rod is 750 and 750, and here there is load of 1500 pounds, which cause the tension in this wooden piece. It will be like this one. Clear? So what we have to find is average normal stress in the wood, and this distance dash line is given. We have to find this B for which shearing stress is 100 psi and bearing stress in the wood. So let's start with the solution. So first step is that in first part we have to find maximum normal stress in wood. Now you can see that due to this tensile load 1500 in this and 1500 in this wood member will be in tension, and in tension what will be the area contributed? So this weight, whole weight 4 minus this diameter into this weight will be the area. So net area will be equal to this width 4 minus diameter. Clear? Diameter into width, because in tension we subtract this whole because only this portion is taking the load. That's why 4 minus this diameter into this width will be the area. So 4 minus 5 by 8 multiplied by width is, you can see width is 1 inch. So this will give you net area, which is 3.375 square inch. We know that average normal stress is equal to load per unit area. So load is given as 1500 tensile force. So 1500 divided by net area is 3.375, which will give you 444 psi. So this is the answer of our first part, that average normal stress in wood is 444 psi. Now we will move toward second part, and in second part, which is distance B, distance B for shearing stress is given as 100 psi. So we know that shearing stress is equal to shearing load per unit shearing area. So from here, load is P, shearing area is this. This load will cause the this shaft, steel shaft, to move in this direction. So shearing area will be this B into thickness T. So I will write B is this distance and thickness T. Okay, we have the shearing area, so B into T will be equal to P divided by shearing stress. We are interested to find out B, so B is equal to P divided by shearing stress into thickness. So P load is given as 1500 divided by shearing area, shearing stress is 100, multiply by thickness T, which is 1. Since we have two shearing area, one it will shear along this and the second one is along this, so we will multiply it with 2. Shearing area will be equal to 2. Okay, so this will be 2 times, so thickness is given as 1 multiplied by 2. So from here you will get this B will be equal to 7.50 inch. So B is equal to 7.50 inch. This is the answer of our second part. And in third part, it is given that in part C, average bearing stress on wood. So we know that average bearing stress on wood is bearing force divided by the bearing area. So bearing area is this one. This is the bearing area. Diameter into thickness T. This is diameter and this is thickness T. So we will write P divided by diameter into thickness T. So you can just put the value. Bearing stress is equal to load is again 1500, diameter is 5 by 8 inch and thickness is 1 inch. So when you calculate it, you will get bearing stress, which comes out to be 2400 psi. And this is the answer of our third part. And that was all about this problem 1-23. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video which I post. And if you have any question, you can ask me in comment section. Thank you for watching and liking my videos. Welcome back. Problem 1.24. So statement is knowing that theta is 40 degree, P is 9 kilonewton. Determine the smallest allowable diameter of pin at B if the average shearing stress in the P not exceed 120 megapascal, and in B part corresponding average bearing stress in member AB at B, and in C part corresponding average bearing stress in each of the support bracket at B. So from this diagram you can see this is member AB, this is roof. Clear, there is a point load of P and the angle which member AB made with horizontal is theta. So you have to find the allowable diameter of this pin at B, you have to first find this diameter, and then in average bearing stress in this member AB, and in each of these bracket bearing stress in each of these support bracket. So let's start with the solution. So from this diagram we can see that this distance of AB is given as 750 and this distance is also 750. So there will be an isosceles triangle. So let's draw it first. So distance between B and C is given. So this is B point, this is C, this distance is 750. A and B is also 750. This is point A, this is also 750. Clear? So we will form an isosceles triangle is ABC. So what we will do is that this angle theta is given as, this angle is theta, which is given as 40 degree. So this is 40 degree and this will be 140 degree. Why? Because the sum of these two angles will give you 180 degree. So 180 minus 40 will be equal to 140 degree. Clear? Now again you can see that there is a point load of P at this point load is P. This load is vertical load and this load is P. Clear? And what we will do is that you can see this is 40 degree. So if I extend it, this is 90. So this angle will be equal to 50 degree. We do not know this angle and this angle. So what we will do is that we will use law of cosine. Law of cosine. So from law of cosine, what does law of cosine says that this side, if you want to find AC, so AC square will be equal to AC square will be equal to AB square plus BC square plus minus 2 times AB into BC into angle between them, which is 140. So cos of 140 degree. So you can put AB is 750, so 750 square plus 750, BC is also 750 square. This is AB and this is BC. Minus 2 times 750 multiplied by 750. You can also write 750 square into cos of 140 degree. That will be equal to AC. And if you take the square root on both sides, so you will get AC. And this AC is equal to 1409 millimeter. So this AC is 1409 millimeter. Now we'll find this theta by using law of sine. Law of sine. What does law of sine says? That if you take this length and opposite to this angle, the ratio of length to this angle, which is 750 divided by sine of theta, will be equal to 1409 divided by sine of 140 degree. Of 140 degree. So from here you will get sine of theta will be equal to 750 multiplied by sine of 140 degree divided by 1409, and you will get theta is equal to sine inverse 750 multiplied by sine of 140 degree divided by 1409. So you will get theta will be equal to 20 degree. Now this angle is 20 degree. I will replace this theta with 20 degree. So this angle will be also 20 degree. And you can see that this is a right angle. So 50 plus theta plus 20 will be equal to 90 degree. So theta will be also 20 degree. So from here we will get this theta is also 20 degree. Now we have this angle, so all these angles, so we will move towards we will take joint A as free body, and we will find the forces acting on joint A. So you can see at point A we have a load of P which is acting downward. So this is P, and this is angle 50. So this angle between okay, the angle between A at this is point A. So angle between P and AB is 50. So this is the angle. This is joint A. This is point A, and this angle between A and P and AB. This is the force AB. This angle is 50 degree, and you can see that this is point P. Clear. So the angle between P and this AC is 90 plus 20, which is equal to 110 degree. So I will take angle between P and FAC is 110 degree. You can see the load is acting downwards, which causes the stress force in loop in this direction, and as per Newton third law, the wire applied a force in this direction, which is FAC. Now we will join this, and we will show it using force triangle. So how you will do that? So this is the P load which is acting downward. Clear. And in FAC okay, so let me show you here. This is the load FAB. Clear. Then we have P, and in return we have FAC. Okay, so force in FAB is in this direction. Clear. Minus P will be in this direction, and so you will get the resultant like this. So let me correct it. First we will draw force in AB. Okay, yeah, or you can say, you can draw first P. This is the P load which is downward. Clear. And the angle between P and FAB is 50. So this is angle 50 degree. This is FAB. So FAB plus P downward is equal to, sorry, kindly correct it. It will be like this. Not a straight line, but it will be like this if I extend it over here. Okay. So this will be F, resultant will be FAC, and this angle is 20. I will also show you, you can see the angle between, this is AB and this is AC, so angle is 20. If you draw it correctly, you will get this angle as 20 degree. Now this is the force triangle. So using law of sine, law of sine, what we can write is that P divided by P, this is P divided by sine of 20 degree will be equal to FAB divided, and this angle is 110 degree. FAB divided by sine of 110 degree is equal to FAC divided by sine of opposite angle, which is 50 degree. Okay, now you can relate these two and these two as well, since we are interested to find out the force in FAB. So what we will do is that we will take PAB, we will take this equation. P divided by sine of 20 degree is equal to FAB divided by sine of 110 degree. So from here FAB is equal to P into sine of 110 degree divided by sine of 20 degree. So put the value P is 9, sine of 110 degree divided by sine of 20 degree. So by using calculator, when you calculate it, FAB comes out to be 24.73 kilo Newton. So this is our required force which we need. Now we will, this force is in this direction, clear? So we will find out first the average bearing stress in member. Okay, the smallest first part is allowable, smallest at point B. So let's move and solve our three parts. So the first part is about allowable pin diameter. Now here you can see that due to this load in member AB, this pin is in this portion and this portion, which will cause the double shear, clear? So we know that allowable pin diameter, we are interested to find allowable pin diameter D. We know that shearing stress is equal to shear force. Now here shear force is FAB. As the pin is double shear, so we will take 2 times of AP. So FAB divided by 2 times, the pin is double sheared, so 2 times area of pin is, if having diameter D, is pi by 4 D square. So from here it will be equal to 2 FAB divided by pi D square. We are finding out D, so D square is equal to 2 FAB divided by pi into tau. Put the value 2 multiplied by FB is 24.73 divided by pi, and allowable shearing stress is given as 120 megapascal. So 120 into 10 raised to power 120 into 10 raised to power 6. Here 24.7 kilonewton, so we will multiply 10 raised to power 3 as well. So D, after taking D square, will be equal to 131.18 into 10 raised to power minus 6 square meter. So D will be equal to, if you take the square root on both sides, so you will get D will be equal to 11.45 into 10 raised to power minus 3 meter, or you can see 11.45 millimeter. So this is the diameter of pin at point B. Now we will move toward our second part, and second part is about the bearing stress in member in AB. So we know that bearing stress is equal to bearing force, which is FAB divided by bearing area. So FA bearing area is, you can see in member AB, this is, let's say, member AB, clear? So this is this forces, so bearing area is this one, D into thickness. So FAB divided by D into T, clear? So you can put the values. FAB is 24.73 into 10 raised to power 3 divided by diameter of pin, diameter of this hole is given, thickness is 16 millimeter and diameter is given as bearing area. Diameter is, which we have calculated, is this one, 4 point. So diameter, thickness is 16 millimeter. So 16 is 0 point, in meter is 0.016 multiplied by diameter is, in meter is 0.011, or you can say you can pick, let me choose rubber, or you can say that you have 11 into 0.45 into 10 raised to power minus 3. So from here you will get bearing stress in member AB comes out to be 134.9 into 10 raised to power 6 or 134.9 megapascal. So this is bearing stress in member BC. In C part, we have been asked to find the bearing stress in support bracket. So bearing stress in support bracket. So again you can see there are two brackets, one is this one and another is this one. So this force FAB will be distributed half 1 over 2 FB in this bracket and half 1 over 2 FBAB in this bracket. So in one bracket, supporting bearing stress is equal to half of FAB divided by bearing area. Clear? So half of 24.73 into 10 raised to power 3 divided by bearing area is D into T. So now you can see this thickness of this bracket is 12. Thickness is 12 and the diameter is 11 point, which we have calculated 11.45. So I will write it 11.45 into 10 raised to power minus 3 multiplied by thickness is 12 millimeter, which is 0.012 meter. So when you calculate, you will get the average bearing stress in supporting bracket comes out to be 90 into 10 raised to power 6, which is 90 megapascal. And this is the answer of our third part, C. And that was all about this problem 1.24. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1.24. In previous problem, we discussed problem 1.24 and this problem is similar to 1.25. The statement is determine the largest load P that can be applied at A when theta is 60 degree, knowing that the average shearing stress in 10 millimeter diameter pin at B must not exceed 120 megapascal and that average bearing stress in member AB and in bracket at B must not exceed 90 megapascal. So you can see this is the figure. This is member AB where P load is applied. These two are the brackets and this is the pin. The diameter of pin is given as 10 millimeter. Average shearing stress in this pin is 120 megapascal and average bearing stress in this member AB as well as in these brackets is given as 90 megapascal. So you have to determine the maximum load P that can be applied at point A. So let's start with the solution. So if you look into this diagram, so you will see that this length is given as 750 millimeter and this length is also 750 millimeter and this roof will also attach. So it will make an isosceles triangle. So from geometry, I will write it. From geometry, triangle ABC, triangle ABC is an isosceles triangle. I will write also this length B into BC is 750 millimeter. So this length is 750 millimeter. This is point B, this is point C, 750 millimeter. And this length AB is again, this is also 750 millimeter. So this is point A, 70 millimeter, and this is the roof AC. Okay, roof AC. Now you can see that we have been given this angle is 60 degree. So this angle will be taken as 60 degree. So remaining this angle will be 120 degree, and this theta will be, this will be theta and this will be theta. Since these are isosceles triangle, two sides are same, so both theta will be same. And you can see that sum of all angles 120 in a triangle is equal to 80. So theta plus theta is equal to 180 degree. So 2 theta is equal to 180 minus 120 degree. So theta will be equal, 2 theta will be equal to 60 degree. It means that one angle is 30 degree. So this theta is equal to 30 degree. I will change it. This will be 30 degree and this will be also 30 degree. Okay, so here you can see you have a point load of P, which we have to find. So from this isosceles triangle, we came to know that this angle is 30 and this is also 30. Okay, now what we will do is that use joint A as free body diagram, A as FBD, which is free body diagram. So at point A, if this is the point A, so you can see you have a load of P which is acting at point A. This load is P, and at point P you can see you have a force FAC. So this force will be in this direction and the other force FAB will be in this direction. Why? Because you can see due to this load, this will go down and the load in wire will be like this. But due to Newton's third law, the rope exert a force on point A will be in this direction. This is FAC. Similarly, FAB will be in this direction. So we will draw it. FAB will make, from here you can also see that FAB is this force. What makes it? It's making an angle of 30 degree over here. Okay, 30 degree with vertical axis. Because you can see if I draw vertical line, so this is 60, this is 90, so this will be also 30 degree. So the angle between A and P and FAB is 30 degree. So I will write it. If I draw this angle is 30 degree. The angle between P and this load FAB is this one, this angle. And this angle you can see this is 90 degree and this is also 30 degree. Clear? Because this is 30, so this will be also 30 degree. So total angle P formed with the AC will be equal to 120 degree. So I have to draw FAC. This is FAC. This is FAB. So this total angle is 120 degree. Now this is the free body diagram at joint B. So using force triangle methods, we will join it by using vector addition. So if you have FAB, okay, so if you have FAB, so if you draw this like this is a horizontal line, and if for reference, and if you draw FAB in this direction, which makes 30 degree with the horizontal. Okay, so this is 30, this is FAB, and then P vertical load. P will be downward. Okay, P will be downward. Let me correct it. P is downward. So P is downward, and you can see if you both add it, or if you the third one is FAC. So again horizontal line, this is 90, so 120 will be this one. Okay, so I will delete this point, this 30 degree. Okay, so this line is 120 degree, 120 degree. Or you can also just draw it like this. Let me do it again so that it be clear. So this is the P force which is acting downward. Okay, so P, the angle between P and A is 30 degree. FAB is 30 degree. So from here you can draw a 30 degree. Clear? So this angle is 30 degree, and this is FAB. And what will be the direction of FAB? FAB will be in towards the P, because you can see over here it will be like this. So third one will be this one. This will be your FAC. Okay. This is FAB. So this is FAC. And this angle, when you draw it, it will be 120 degree. Now this is again the angle between FAB and FAC is 30 degree. You can see here this is also 30 degree, or this angle between AB and AC is 30. Now we will use law of sine for finding. What law of sine says that if we take P divided by sine of 30, it will be equal to FAB divided by 120, or FAC divided by sine of 30. So I will write P divided by sine of 30 degree will be equal to FAB over sine 120 degree, or it will be also equal to FAC over sine of 30 degree. If you equate these two, so these two, if I write it, P divided by sine of 30 degree is equal to FAB over sine of 120 degree. So from here you will get P will be equal to FAB into sine of 30 divided by sine of 120 degree. And from here you will get this P will be equal to 0.57735 times FAB. So this is one formula for P. Clear? Now if you take these two, equate these two, so we will get P over sine of 30 will be equal to FAC over sine of 30 degree. So from here you will get P is equal to FAC into sine of 30 degree divided by sine of 30 degree, which will give you P is equal to FAC. We are interested to find out P, and here the answers will start from here, because we are interested to find out P. So we have the bearing stress in this members, shearing stress in this pin, and bearing stress in this brackets. So we will take FAB as in our calculation. So we will first find FAB. So what we will do is that first it is given that average shearing stress in pins. So our criteria will be, first, if shearing stress in pin at B controls. So if we take the shearing stress in pin B, so what will be the value of FAB? So we know that shearing stress is equal to shearing force per unit area. So you can see that here this pin will be shear over here as well over here. So there are two double, due to double shearing. double shear of the pin. We will take 2a. So shearing stress is equal to force divided by 2a because due to double shears. So shearing stress is given as 120 megapascal. Clear? So an area of pin. So area of pin is equal to pi by 4 d square. Area d diameter is given as 10 millimeter, which is 0.010 meter square. So from here you will get 78.54 into 10 raised to power minus 6 square meter. This is the area. So we are interested to find out F. So F will be FAB because in pin FAB force is acting. So FAB will be equal to shears multiplied by 2 times area. Shearing stress is 120 megapascal. So 120 multiplied by 10 raised to power 6 multiplied by 2 multiplied by this area, which is 78.54 into 10 raised to power minus 6. So you will get FAB will be equal to 18.850 into 10 raised to power 3 Newton. So this is the force that is produced in the pin due to the shearing stress of 120 megapascal. Now what we will use another criteria, and in another criteria it is given if bearing stress in member AB controls. So what we will do is that we have given the bearing stress in this member AB, which is 90 megapascal. So you can see here that this member will have this hole in which this pin will pass. So the bearing area will be AB will be equal to diameter into its thickness. Diameter is the diameter of this pin will be the diameter of hole in this rod, and thickness is given as 16 millimeter. So we will write bearing stress is equal to FAB divided by AB. So FAB, we are interested to find out FAB. So FAB will be equal to bearing into AB. So bearing stress is 90 megapascal, 90 to 10 raised to power 6 into AB is D into T. So diameter is 0.01 and thickness is given as 16 millimeter. Okay, 16 millimeter, which is 0.016. So from here you will get FAB will be equal to 14.40 into 10 raised to power 3 Newton. So this is the force that is due to bearing stress in member AB. Now the third criteria which I will write over here is, I will draw a line. If bearing stress in bracket controls. So we know that bearing stress is equal to force divided by bearing area. So you can see that we have two bracket. One is this one, another one is this one. So area 2 times area. So FB divided by 2 times AB. And AB, you can see that AB is equal to diameter of hole into its thickness. So thickness of this is 12. This thickness is 12 and this diameter is 10 millimeter. Okay. So what we will write is that D into T. So 2D is 0.01 and thickness is 0.012. So if you put the values over here, let me solve it over here. So bearing stress will be equal to FAB because bearing stress is due to this FAB. So FAB will be equal to 2 into sigma B into AB. So you can just put the values of sigma b, so FAB will be equal to 2 times sigma is 19 to 10 raised to power 6 and AB is 0.01 multiplied by 0.012. When you solve this, you will get FAB will be equal to 21.6 into 10 raised to power 3 Newton. Now this is the force that is produced in brackets. Clear? So you have three forces. The first one is this one, the second one is this one, and third one is this one. That is calculated based on different criteria. Here the criteria was shear stress, here the bearing stress in member AB, and here the bearing stress in the bracket. So what we will do is that we have to choose one of this, so we will choose the smallest force FAB. So smallest will be this one, 14.40, because it will be safer. Always we will choose the smallest force so that our design will remain safer. Now this is the force we have selected, and we know that from this equation that P is equal to 0.57735 times FAB. So you can just multiply 0.57735 multiply by 14.40 into 10 raised to power 3. So you will get the value of P comes out to be 8.31 into 10 raised to power 3 Newton. Or you can say P is equal to 8.31 kilonewton. So this is the largest amount of force which is safer and that can be applied at point A, at this point. And that was all about this problem 1.25. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 1.26. So statement is link AB of width B 50 mm and thickness 6 mm is used to support the end of a horizontal beam, knowing that average normal stress in the link is minus 140 megapascal and the average shearing stress in each of the two pin is 80 megapascal. Determine A, the diameter of D of the pin, and B, average bearing stress in the link. So this is a horizontal beam that is supported by this link AB having two pins that is used to support this horizontal beam, and the width of this link is 50 millimeter and thickness is 6 millimeter. And due to this support, there is a compressive stress. Sigma is equal to average sigma is equal to 140 megapascal. Here it is given as minus 140, so 140, and this arrow shows that this is in compression. Negative sign means compression. So you have to determine the diameter of this pin B having average shearing stress is 80 megapascal, and then you have to find the average bearing stress in this link AB. So let's start with the solution. So as we have discussed that this rod, this link AB is in compression, so this will be P. Due to stress, this will be the P. Okay, so this link AB is in compression. Sigma is given as sigma average in link is given as 140 megapascal. I have removed the negative sign because negative sign shows compression. We know that normal stress is equal to load per unit area. Okay, so we have area of this link. This area is equal to, in compression we neglect this hole in this link, because in compression this hole will also compressed. So the net area will be equal to this width into thickness. So A will be equal to B multiplied by T. So B is 50 millimeter, which is 0.050, and thickness is 0.006 meter. So when you multiply it, you will get 300 into 10 raised to power minus 6 square meter. Now what we will do is that we have average normal stress in this link. So this P will be equal to sigma average multiplied by area. So sigma average is 140 megapascal. 140 into 10 raised to power 6 multiplied by area, which is 300 multiplied by 10 raised to power minus 6. So P will be equal to, load will be equal to 42 into 10 raised to power 3 Newton. And this load will be also a compressive one, because this compressive load will cause the compressive stress. Now you have P. We will move toward first part for pin. We know that average shearing stress in pin is equal to load divided by shearing area. So here the shearing area is this. This shearing area will be this one. Okay, so that is for pin we have area is pi by 4. Area will be equal to, area of pin will be equal to pi by 4 d square. We have d is 0 pi by 4. D is diameter is 0.006. Clear? And okay, sorry, diameter of pin is not given. Okay, so we have diameter of area of pin is equal to pi by 4 d square, and we know that average shearing stress is P by A. So from here you will get A is equal to P by shear stress. So P is 42 into 10 raised to power 3, which we have calculated earlier, divided by shearing stress is given as 80 megapascal. So 80 into 10 raised to power 6. So when you calculate it, you will get area of pin will be equal to 525 into 10 raised to power minus 6 square meter. Now area of pin is equal to pi by 4 d square, and that is equal to 525 into 10 raised to power minus 6. So from here we will get d square is equal to 4 multiplied by 525 into 10 raised to power minus 6 divided by pi, which is 3.1417. And if you take the square root on both sides, so you will get d will be equal to, after calculation, it will be 2.585 into 10 raised to power minus 3 meter. Or you in millimeter, it is equal to 2.59 millimeter. So this is the answer of our first part. And in part B, we have been asked to find the average bearing stress in the link. So average bearing stress in the link is equal to bearing stress, not normal stress. So load divided by bearing area. So bearing area is this one, this whole diameter into thickness. Clear? This is the bearing area. So diameter we have calculated, and thickness is this one, which is 6 millimeter. So put the value P is equal to 42 into 10 raised to power 3 divided by bearing area is diameter, which we have calculated 2.59 into 10 raised to power minus 3 multiplied by thickness is 0.006. So when you calculate it, you will get the bearing stress in link AB comes out to be 271 into 10 raised to power 6 Pascal. Or you can say that bearing stress in link AB is 271 megapascal. So this is the answer of our second part. And that was all about this problem 1.26. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.